A single star can outshine an entire galaxy, and the supernova that does it rewrites our view of the cosmos. Stay tuned, because number 1 is a blast nobody predicts. Imagine a star that shines brighter than an entire galaxy for months, dwarfing every other supernova we have catalogued. SN 2006 GY erupted in a distant spiral galaxy and maintained a luminosity roughly 10 times that of typical supernovae, keeping astronomers glued to their telescopes for an unprecedented duration. Researchers estimate it released energy equivalent to billions of suns, suggesting the progenitor was an extremely massive star that shed a dense shell of material before exploding. This extraordinary brightness challenges conventional models of stellar death, hinting at exotic mechanisms like parinstability explosions. The lingering glow also provided a rare laboratory for studying how such intense radiation interacts with surrounding interstellar matter, offering clues about galaxy evolution. Up next, we turn to a supernova that lit up our cosmic backyard, making it the closest type Ia in decades.
Bursting onto the scene in the heart of Messier 82, SN 2014J became the brightest type Ia supernova observed in over 40 years, visible even to casual stargazers with modest equipment. Its proximity, just 11.5 million light-years away, allowed scientists to capture high-resolution spectra within hours, refining measurements of the universe's expansion rate. The event also sparked debates about the exact composition of the exploding white dwarf, as subtle variations in its light curve hinted at possible differences in progenitor systems. By comparing its brightness to theoretical models, astronomers tightened the constraints on dark energy's influence over cosmic acceleration. The wealth of data from SN 2014J continues to feed into calibration efforts for future distance ladder studies. Next, we explore a supernova that linked a stellar explosion to a powerful gamma-ray burst, reshaping high-energy astrophysics.
In 1998, astronomers witnessed a supernova that seemed to dance with a gamma-ray burst, forging the first solid connection between these two extreme phenomena. SN 1998 BW, located in a dwarf galaxy, coincided with GRB 980425, an unusually low-energy burst that nonetheless released a focused jet of high-energy photons. The supernova's spectra displayed unusually broad absorption lines, indicating ejecta moving at speeds up to 30,000 km per second, far faster than typical core collapse events. This hyperenergetic explosion, sometimes called a hypernova, suggested that some massive stars can produce both a spectacular supernova and a relativistic jet. The dual detection offered a rare window into the engine-driving gamma-ray bursts and hinted that such events might contribute significantly to the synthesis of heavy elements. Up next, we examine the first-ever observed shock breakout, a fleeting flash that reveals the moment a star's interior bursts through its surface.
Few people know that SN 2008D gave us the first glimpse of a supernova's shock breakout, a flash of X-rays that lasts only minutes as the explosion's shockwave pierces the star's outer layers. Detected serendipitously by the Swift satellite while observing a different gamma-ray burst, the X-ray burst signaled the exact moment of core collapse in a distant galaxy. Follow-up observations tracked the evolving optical light curve, allowing researchers to map the progenitor's size and composition with unprecedented precision. The shock breakout's brief brilliance confirmed theoretical predictions about how energy propagates through stellar envelopes, and it opened a new observational window for catching supernovae in the act. Soon after, we'll look at a supernova that became the benchmark for calibrating cosmic distances, thanks to its crystal-clear view in a nearby spiral galaxy.
Hidden within the Pinwheel Galaxy, SN 2011 Phi became the gold standard for measuring cosmic distances, offering a pristine laboratory for Type Ia supernova research. Discovered just hours after explosion, its proximity, about 21 million light-years, allowed astronomers to capture a complete set of spectra from ultraviolet to infrared, minimizing uncertainties caused by dust or intervening material. The supernova's light curve matched theoretical expectations almost perfectly, reinforcing the reliability of Type Ia events as standard candles for mapping the expansion of the universe. Moreover, early observations of the progenitor's environment suggested the exploding white dwarf had a companion star, providing valuable clues to the long-standing debate over single versus double degenerate scenarios. This wealth of data continues to refine calculations of the Hubble constant. Next, we venture into a faint yet informative explosion that challenged assumptions about the lower limits of supernova brightness.
Deep beneath the surface of a red supergiant, SN 2005 CS surprised scientists with its unusually low brightness, classifying it as a low-luminosity Type 2P supernova. Despite originating from a massive star, the explosion released only a fraction of the energy typical for its class, leading to a plateau in its light curve that was both dimmer and shorter than expected. Detailed modeling suggests the progenitor may have shed much of its outer envelope before collapse, or that the core collapse mechanism was somehow inefficient. This subdued event provided a crucial data point for understanding the diversity of core collapse supernovae and the role of mass loss in shaping final outcomes. By comparing SN 2005 CS to brighter cousins, researchers refined estimates of how often such faint explosions occur, influencing predictions of supernova rates in distant galaxies. Up next, we spotlight a supernova caught within hours of its birth, offering an unprecedented early view.
Surprisingly, SN 2016 GKG was spotted within hours of its explosion, offering a rare early view that illuminated the initial moments of a stellar death. The rapid detection, enabled by high-cadence surveys, captured the rise of the light curve from the very first photons, allowing astronomers to infer the radius of the progenitor star, a compact, stripped-envelope star roughly the size of the Sun. Spectroscopic data revealed a thin layer of hydrogen, suggesting the star had lost most of its outer layers prior to collapse. This early insight helped test theoretical models of shock cooling and the role of binary interactions in shaping progenitor evolution. The event also underscored the importance of continuous sky monitoring for catching transient phenomena at their inception. Coming up, we explore a supernova that appears to have broken the Chandrasekhar limit, challenging fundamental physics.
Remarkably, SN 2003 FG appears to have exceeded the Chandrasekhar limit, the theoretical maximum mass for a stable white dwarf, thereby challenging our understanding of type Ia progenitors. Its peak luminosity was significantly higher than typical, and its spectral features indicated a larger amount of nickel 5-6 synthesized during the explosion, roughly 1.3 solar masses, well above standard estimates. Some researchers propose that the white dwarf merged with a companion, creating a supermassive object that ignited in a thermonuclear runaway. Others suggest rapid rotation could have temporarily supported the excess mass. This extraordinary case sparked vigorous debate about whether multiple pathways exist for type Ia explosions, a question that directly impacts the reliability of these supernovae as cosmological distance markers. Up next, we examine a transitional supernova that blurred the lines between established categories, reshaping classification schemes.
We've journeyed through 10 astonishing stellar catastrophes, each pushing the boundaries of what we thought possible and teaching us how the universe recycles its own material. These record-breaking supernovae not only illuminate distant galaxies but also seed the cosmos with the elements that make planets, and life, possible. If you enjoyed uncovering these cosmic milestones, hit the like button and subscribe so you never miss the next mind-blowing list we drop each week. Which explosion surprised you most, and why? Share your thoughts in the comments below. I love hearing your perspectives.